Europa has been lying to us, not in a subtle way, not in the way science quietly revises its assumptions over decades, in the most dramatic way possible, by hiding an entire ocean. For decades, we looked at this moon and saw a frozen wasteland, a smooth, pale ball of ice orbiting Jupiter, pretty in photographs, scientifically polite, unremarkable in every way that should matter. Scientists discussed it the way you discuss a colleague's vacation photos at the office. Nice, interesting, moving on. There were conferences, there were papers, there were cautious, carefully worded sentences about potential habitability and conditions possibly suitable for microbial life. All of it so measured, so academic, so deliberately underwhelming that the average person had no idea Europa was one of the most consequential objects in the entire solar system. And then James Webb looked at it, and everything changed. In the last 18 months, the James Webb Space Telescope has been quietly, methodically, patiently pulling back the curtain on what Europa actually is. Not what we assumed, not what our models predicted, what it actually is, and what it found. What Webb saw in the infrared glow of that frozen surface more than 600 million kilometers from Earth is not normal. It is not what anyone expected, and it may be the most important thing a telescope has ever seen. Let's start with what we thought we knew, because that's where the cracks are widest. Europa is one of Jupiter's 4 Galilean moons, discovered in 1610 by Galileo Galilei himself. Think about that for a moment. A man with a crude brass telescope peering at the night sky 400 years ago, and he stumbled onto one of the places in the universe most likely to harbor life beyond Earth. He didn't know that, of course. He just saw a tiny dot moving around Jupiter. But that dot turned out to be roughly 3,100 kilometers across, slightly smaller than our own moon, and it is anything but ordinary. From the outside, Europa looks like a cracked egg. The surface is almost entirely water ice, swept clean by geological processes and Jupiter's relentless radiation, crisscrossed with reddish-brown streaks and ridges that stretch for thousands of kilometers. These lines aren't cracks in the way you'd imagine on a dry, frozen world. They're scars, evidence of an internal system so dynamic, so restless, so alive with energy that it physically tears the surface apart and reheals it from below. And beneath that ice, there is an ocean. We've suspected that since the late 1990s, when NASA's Galileo spacecraft measured subtle but unmistakable disruptions in Jupiter's magnetic field near Europa. Disruptions that could only be explained by one thing: a vast body of electrically conductive liquid beneath the surface. Salt water, an entire global ocean of it. Scientists estimate it likely contains more liquid water than every ocean on Earth combined, perhaps 2 to 3 times as much, sealed under a shell of ice that could be anywhere from 10 to 30 kilometers thick, depending on where you look and which model you trust. That ocean is what made Europa famous. Where there is liquid water, there is at least the possibility of life. Not a guarantee. Not even a strong hint. Just a door left slightly open. A whisper of possibility in the cold dark of the outer solar system. And for 20 years, that open door was essentially all we had. We couldn't see through the ice. We couldn't taste the water. We couldn't measure what was dissolved in it, or whether the chemistry down there had organized itself into anything interesting, or whether the ocean floor was hot, or cold, or bare, or teeming. We were stuck outside, pressing our faces against frosted glass, fogging it up with our breath, squinting at shadows. James Webb changed that. Not by drilling through the ice, not by landing a probe, not by doing anything dramatic or expensive or years away from completion. Webb changed that by doing something deceptively, almost insultingly simple. It stared at Europa's surface with the most sensitive infrared instruments ever built and read the chemical fingerprints of what was actually there. Like a forensic scientist dusting a crime scene for prints, Webb read the molecules written into the ice by whatever was happening underneath. The carbon discovery that rewrote everything. In September 2023, two independent research teams published results from Webb's near-infrared spectrograph, an instrument so precise it can identify individual molecular compounds on a surface more than 600 million kilometers away. Let that sink in. We are talking about detecting specific chemicals on the surface of a moon orbiting Jupiter, using light that has traveled across the void of space for nearly an hour. The engineering achievement alone is staggering. Both teams were looking for one thing in particular: carbon dioxide. Not because carbon dioxide is exciting on its own. It's in your breath right now. It's in your soda. It's unremarkable chemistry. But on Europa, carbon dioxide is a detective story, because it could come from two entirely different sources. Source 1, external delivery, meteorite impacts, radiation from space, random cosmic chemistry raining down on the surface over billions of years. If the carbon dioxide came from outside, it tells us almost nothing about the ocean below. It's just background noise from space. Source 2, internal origin, the ocean itself. Carbon dissolved in Europa's subsurface sea, pushed upward through cracks in the ice by geological processes, deposited on the surface like condensation on a cold window. If the carbon dioxide came from inside, if it came from below, it means the ocean contains carbon. And carbon is the backbone of every known form of life in the universe. Both teams found it. Carbon dioxide, concentrated, specific, localized in a region called Terra Regio, a geologically young area of disrupted terrain on Europa's trailing hemisphere. Not a thin, random dusting that could be explained away as meteorite contamination. Not scattered uniformly the way external deposition would predict. Concentrated in exactly the kind of terrain that geological models predict would be refreshed by material welling up from below. The distribution pattern pointed downward, toward the ocean. Geronimo Villanueva, the lead author of one of the studies and a planetary scientist at NASA's Goddard Space Flight Center, was measured but unambiguous. The carbon dioxide was not arriving from outside. It was consistent with an internal origin. The ocean beneath Europa's ice contains dissolved carbon dioxide, and the geological churning of Terra Regio had brought traces of it to the surface, like a stain seeping through fabric. Like the ocean was leaving a signature in the ice. Like it was trying to communicate. Carbon in a subsurface ocean is a prerequisite for the kind of chemistry that could, in theory, support life as we understand it. Carbon-based organic chemistry, the chemistry of amino acids, of nucleic acids, of metabolism, requires carbon as its skeleton. No carbon, no biochemistry as we know it. Carbon in Europa's ocean means that one of the fundamental requirements for life is present in that hidden sea. But Webb wasn't finished. In March 2024, a separate team used Webb to search for something even more dramatic: plume activity. Jets of water vapor erupting from Europa's surface directly into space. The Hubble Space Telescope had reported possible plumes back in 2012 and again in 2016. But the detections were shaky, right at the edge of Hubble's capability, where instrument noise and real signal blur together. Some scientists believed them, others weren't convinced. The debate had been simmering for almost a decade without resolution. Webb looked, and this time the answer was clearer. No large, persistent plumes were detected during the observation window. That might sound like a disappointment. It isn't. What it tells scientists is that Europa's plume activity, if it exists, is likely sporadic rather than constant. Enceladus, Saturn's tiny moon, fires geysers continuously from its south pole, fed by tidal forces kneading its interior like bread dough. Europa appears to work differently. Its outbursts, if they happen, are intermittent, possibly triggered by specific tidal stresses, as Jupiter's immense gravity flexes the moon's ice shell during its elliptical orbit. The plumes aren't gone. They're just unpredictable, waiting for the right moment. Where does the energy come from? Here's the question that haunted planetary scientists for decades before they found the answer. Europa is 780 million kilometers from the Sun. At that distance, solar heating is negligible. The surface temperature sits around minus 160 degrees Celsius, cold enough to freeze nitrogen into slush. By every surface measurement, by every straightforward calculation, this moon should be frozen solid all the way through, an inert ball of ice and rock drifting in the dark. So why isn't it? The answer is Jupiter itself, and it's one of the most elegant mechanisms in the solar system. Europa's orbit isn't perfectly circular. It's slightly elliptical, nudged into that shape by the gravitational tug-of-war between Jupiter and the other large moons, particularly Io and Ganymede. As Europa moves closer to and farther from Jupiter during each orbit, the planet's immense gravity doesn't just pull uniformly. It squeezes and stretches the moon's interior, compressing it from one side, then the other, in an endless rhythmic kneading that generates heat through friction deep inside the rock. This is tidal heating, the same fundamental mechanism that turns Io into the most volcanically active body in the entire solar system. A world where hundreds of volcanoes erupt simultaneously, where lakes of molten sulfur dot the landscape, where the surface is being constantly recycled by lava flows. On Io, tidal heating is so extreme, it's almost cartoonish. On Europa, the effect is far more subtle, but still powerful enough to maintain a liquid ocean for billions of years beneath kilometers of ice. Think of it this way. Take a rubber ball, flex it rapidly in your hands, bend it, compress it, let it spring back, repeat. The ball gets warm. You're converting mechanical energy into heat through the internal friction of the rubber's molecular structure. Now imagine that the ball is 3,100 kilometers wide, and the hands squeezing it belong to the largest planet in the solar system, with a mass 318 times that of Earth. The heat generated by that constant, relentless flexing doesn't just maintain liquid water. It could drive hydrothermal activity on the ocean floor. Hot vents where mineral-rich water at hundreds of degrees meets the cold ocean above, creating chemical gradients that have, on Earth, supported entire ecosystems without a single photon of sunlight. Hydrothermal vents on Earth are not marginal environments. They're thriving communities. Tube worms 2 meters long, blind shrimp, vent crabs, chemosynthetic bacteria that form the base of food chains that owe nothing to the sun. When scientists first discovered these communities in 1977, aboard the research submersible Alvin, diving into the Galapagos Rift, it was not just a biological discovery, it was a philosophical earthquake. Life didn't need sunlight. Life didn't need photosynthesis. Life needed water, chemical energy, and time. That was the complete list. Europa has all three. The discovery of hydrothermal vent ecosystems fundamentally expanded what biologists call the habitable zone, the range of conditions under which life can exist. Before 1977, the assumption was that all life ultimately traced its energy back to the sun. Photosynthesis at the base of every food chain, sunlight as the non-negotiable prerequisite. Vent communities demolished that assumption in a single dive, and the implications for astrobiology, for the search for life beyond Earth, have been reverberating through the scientific community ever since. If life doesn't need sunlight, then habitability doesn't require proximity to a star. It requires water, heat, and chemistry. Suddenly, the universe got a lot more crowded with potential. Current estimates put Europa's ocean at somewhere between 60 and 150 kilometers deep. The deepest point in Earth's oceans, the Mariana Trench, bottoms out at about 11 kilometers. Europa's ocean could be more than 10 times deeper, contained inside a moon smaller than ours, wrapped in ice, heated from below by a gas giant's gravitational embrace. And at the bottom of all that water sits a rocky silicate floor. Not a layer of high-pressure ice like you'd find inside Ganymede. Rock, in direct contact with liquid water. That matters enormously. Rock is where the minerals come from. Rock is where the chemical gradients form. Rock heated by tidal energy and bathed in ancient ocean water is where hydrothermal vents happen. It's where the chemistry starts. It's where, on Earth, nearly 4 billion years ago, something happened that we still don't fully understand, but whose descendants are reading these words right now. Webb's carbon dioxide discovery slots directly into this picture. If the ocean floor is hydrothermally active and the ocean contains dissolved carbon and other compounds, then Europa has 3 of the 4 ingredients that astrobiologists consider necessary for life as we understand it: liquid water, chemical energy, and organic chemistry. The 4th ingredient is time, and Europa has had billions of years. The ocean is estimated to have existed for at least 1 to 2 billion years, possibly longer. For context, complex multicellular life on Earth appeared roughly 600 million years ago. Simple microbial life appeared nearly 4 billion years ago. Europa's ocean has been liquid for longer than the fossil record of life on Earth. The salt story. When researchers examined Webb's spectral data more closely, they found something that hadn't made as many headlines as the carbon dioxide, but was perhaps equally significant. The carbon dioxide wasn't alone. It was mixed with salts, specifically sodium chloride and magnesium sulfate, table salt and Epsom salt, sitting on the surface of a moon 600 million kilometers away. These are exactly the kinds of salts dissolved in Earth's oceans. Their presence in the same regions as the carbon dioxide isn't coincidental. It paints a picture of a system in intimate communication. The ocean talks to the ice. The ice eventually talks to the surface. And the surface, bathed in Jupiter's radiation, talks to space. Webb caught that conversation mid-sentence, decoded one line of it, and realized it was a letter from an ocean that had been sealed away for billions of years. Consider what it means to find these specific salts. Sodium chloride, ordinary table salt, doesn't just appear in oceans by accident. On Earth, it enters the ocean through geological processes, water dissolving rock, running over mineral-rich terrain, carrying ions down into the sea where they accumulate over billions of years. If Europa's ocean contains sodium chloride, it tells us something fundamental. The ocean has been in prolonged contact with rock. The seafloor isn't just there, it's being chemically eroded. Minerals are being leached from it. The ocean is actively interacting with its rocky bottom in ways that have direct implications for chemistry, for energy, for habitability. Magnesium sulfate, Epsom salt, is similarly significant. On Earth, magnesium sulfate appears in environments where sulfur-bearing rocks are oxidized by water. It's a mineral fingerprint of specific geochemical processes. Its presence on Europa's surface, mixed with the carbon dioxide and the sodium chloride, suggests that whatever is happening at the ocean floor involves oxidation-reduction chemistry, exactly the kind of electron exchange reactions that power life on Earth, not just water over rock. Active chemistry, driven chemistry. The salt composition feeds directly into models of ocean habitability. On Earth, hydrothermal vents produce specific ratios of dissolved minerals depending on the temperature and chemistry of the rock they interact with. Different vent fields have different chemical signatures depending on the rock type they're hosted in and the temperature of the circulating fluid. If Europa Clipper can measure the precise salt ratios on Europa's surface and correlate them with what tidal heating models predict for seafloor conditions, scientists will be able to estimate the temperature and chemical environment of the ocean floor without ever touching it. They'll be reading the ocean's diary from the outside cover. In late 2024, additional Webb observations revealed something else. Crystalline water ice features on Europa's surface that appeared fresher than expected. Ice exposed to Jupiter's radiation for any length of time gets damaged. its crystal structure disrupted by charged particles, converting from organized crystalline form to disordered amorphous ice. Fresh crystalline ice on the surface means it was recently exposed, material from below replacing the irradiated surface layer. The distribution of this fresh ice correlates with the same disrupted terrain where the carbon dioxide was found, Terra Regio and adjacent chaotic terrain regions. This is not a coincidence. This is a pattern. Whatever is happening underneath that ice is still happening, right now. The chemistry Webb detected isn't a fossil. It isn't the record of ancient processes that stopped working a billion years ago. It's a bulletin. It's live data from an active system. Europa is communicating through its ice, slowly, geologically, in the language of chemistry and crystal structure. And Webb has learned enough of that language to understand the first few words. The radiation paradox. Here's where Europa gets genuinely strange, where the physics starts bending in directions that feel almost designed. Jupiter bombards Europa's surface with intense radiation, charged particles accelerated to enormous energies by the planet's magnetic field, one of the most powerful in the solar system. This radiation is lethal. We'll come back to what it would do to a human being. The numbers are not comfortable. But for now, focus on what it does to chemistry. At the surface, Jupiter's radiation destroys. It rips complex organic molecules apart. Any biosignature that reaches Europa's surface from the ocean below, any amino acid, any complex carbon compound, any molecular fingerprint of biology, would be chemically demolished within decades. Shredded by charged particles, broken down into simpler fragments, effectively erased before any spacecraft could detect it from orbit. That sounds catastrophic for the search for life. But wait. When radiation splits water ice and other surface molecules into fragments, those fragments don't disappear. They recombine into new compounds. One of the most important products of this radiation chemistry is hydrogen peroxide. Another is molecular oxygen. And here is where the paradox becomes almost poetic. Some models suggest that this radiation-produced oxygen could be cycled back down through the ice into the ocean below, carried by geological processes that slowly incorporate surface material into the subsurface, and from there into the ocean, where it would be available as a chemical energy source for any organisms that might exist there. Jupiter's radiation, which sterilizes the surface and destroys organic chemistry in plain sight, might simultaneously be feeding the ocean. The death ray from above could be the food delivery system from below. When I first understood this feedback loop, it stopped me cold. A planet that showers its moon with lethal radiation, and that radiation, filtered through 30 kilometers of ice and transformed by geological processing, might arrive at the ocean as oxidants, as fuel, as the chemical equivalent of oxygen that life on Earth uses to power its metabolism. Europa doesn't play by intuitive rules. The chaotic terrain, a window into the deep. About a quarter of Europa's surface is covered in what scientists call chaotic terrain, zones where ice blocks have been jumbled, tilted, rotated, and refrozen at strange angles, like a massive frozen jigsaw puzzle thrown in the air and caught in mid-fall. These regions have fascinated scientists for decades because they look like nothing else in the solar system. The leading explanation is subsurface destabilization. Warm ice, or pockets of liquid water, rise from below, soften the overlying ice from underneath, causing the surface to collapse inward in a disordered way, then refreeze in whatever configuration gravity demands. It's essentially an ice version of the geological process that creates sinkholes on Earth, but driven by heat from below rather than collapsing groundwater voids. If that model is correct, and Webb's carbon dioxide data makes it more compelling, then the chaotic terrain regions are geological chimneys. Pathways through which ocean material rises, gets incorporated into the ice shell, migrates toward the surface, and eventually deposits on top. The carbon dioxide in terra regio wasn't carried there slowly over billions of years. It was transported relatively quickly by a convective process cycling ocean chemistry toward the surface in geological bursts. That's not a dead moon. That's not a frozen relic of an ancient, long-cooled world. That's a moon with an active internal circulation system. A moon that is, in a very real sense, geologically alive, even if we don't yet know whether it is biologically alive. Clipper's ice-penetrating radar, called REASON, will test this model directly. By mapping the internal structure of the ice shell down to about 30 kilometers depth, REASON should be able to detect liquid water pockets trapped within the ice itself, subsurface lakes sandwiched between the frozen surface and the deep ocean below. If those lakes exist, they would dramatically expand Europa's habitable volume. Water wouldn't just be in the deep ocean, 60 to 150 kilometers down. It could be in reservoirs relatively close to the surface, accessible to future landers that don't need to penetrate 30 kilometers of ice. Think about what that means for exploration. Think about what that means for life. Europa. Clipper, the mission that will answer the question. NASA's Europa Clipper launched in October 2024, and it is carrying the most sophisticated suite of scientific instruments ever sent to the outer solar system. 9 instruments, designed specifically to interrogate Europa in ways that ground-based and even orbital telescopes cannot. Each one built to answer a specific piece of the question that Webb has been helping to frame. Clipper won't arrive at Jupiter until 2030. 6 years of transit across the solar system, following a carefully calculated trajectory that uses gravity assists from Mars and Earth to build up the speed needed to reach the outer planets without carrying an impossible amount of fuel. When it arrives, it won't park in orbit around Europa. It can't. Jupiter's radiation belt would fry its electronics within weeks, even with the spacecraft's elaborate shielding. Instead, Clipper will execute roughly 50 close flybys of Europa, dipping down to within 25 kilometers of the surface on the closest passes, before retreating to safer distances to transmit data and let its instruments recover. 50 flybys instead of a stable orbit, because parking at Europa would be suicide for the spacecraft. The radiation environment that makes the surface lethal to unshielded humans is also lethal to unshielded electronics. Clipper's electronics sit inside a titanium vault with walls nearly a centimeter thick, what engineers call the radiation vault, designed to reduce the radiation exposure to its sensitive components by a factor of nearly 800. And even with that armor, mission designers have to be careful about how long Clipper spends near Europa during each pass. One of Clipper's 9 instruments is called SUDA, the Surface Dust Analyzer. Its job is to catch and analyze microscopic grains of ice and dust ejected from Europa's surface by micrometeorite impacts or any plume activity that occurs during the flybys. Each grain is essentially a tiny frozen sample of whatever material sits on or just below the surface. SUDA can determine the molecular composition of individual grains, meaning it doesn't need a dramatic Hollywood-style eruption to get useful data. Even the faint haze of particles kicked up by routine surface micrometeorite impacts is enough. One instrument, one grain, one molecule detected that doesn't belong to simple inorganic chemistry, and the entire conversation about what's in Europa's ocean changes permanently. Webb's carbon dioxide detection at Terra Regio didn't just confirm that the ocean contains carbon, it gave Clipper a target. The disrupted terrain, the carbon signature, the geological youth of the surface, all of it points to a place where the ocean is communicating with the surface. Clipper's job, in part, is to fly through that communication as closely as possible and decode it at ranges and resolutions that make Webb's distant stare look blurry by comparison. The JUICE mission and the power of redundancy. Meanwhile, the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and is on its own long trajectory to the Jupiter system. JUICE will focus primarily on Ganymede, becoming the first spacecraft to orbit a moon other than our own. But it will conduct 2 flybys of Europa as well, adding its own set of instruments to the growing scientific assault on this enigmatic world. JUICE and Clipper carry complementary instruments, not identical ones. They will cross-check each other's data, confirm each other's findings, and fill in each other's gaps. In planetary science, this kind of redundancy isn't waste. It's insurance against the kind of ambiguity that plagued the Hubble plume detections for a decade, where the signal was real enough to publish, but not strong enough to convince everyone. 2 missions, 2 independent data sets, 2 chances to get it right. If Terra Regio is leaking ocean material to the surface, both missions will see it. If there are organics embedded in the ice, Clipper's mass spectrometer will identify them. If there are active plumes erupting during a flyby, one of 9 instruments will catch them. The net is being cast wide, and it's being cast carefully. The philosophical weight of all this. There's a philosophical dimension to what Webb and Clipper represent that I think gets lost in the press releases and the technical jargon and the carefully managed scientific language. For most of human history, the question of whether life exists beyond Earth was a matter for theologians and philosophers. It wasn't a scientific question because we had no tools to investigate it. You could believe in life on other worlds. You could write poems about it. You could argue about it over dinner. You could let it haunt your dreams. But you couldn't test it. You couldn't design an experiment. You couldn't build an instrument. You couldn't point something at the sky and say, "Let's find out." And then we built telescopes. We sent probes. We landed on Mars and found a cold desert punctuated by evidence of ancient rivers. We mapped Venus and found a furnace with an atmosphere dense enough to crush steel. We cataloged the moons of the outer planets and found volcanic Io, moon-sized Titan with its lakes of methane, ancient Ganymede with its own magnetic field, and, quietly, insistently, Europa with its hidden ocean. Slowly, without anyone announcing a ceremony for it, the question shifted. Not is there life out there, but are the ingredients there? That's a question you can answer with a spectrograph. That's a question Webb is answering right now. Carbon? Confirmed. Water? Confirmed. Energy? Confirmed. Time? Billions of years. The checklist grows shorter. I keep coming back to Terra Regio because it is the geographic centerpiece of everything Webb has told us. Relatively young, geologically speaking. Its surface has been reworked, broken apart, and reassembled by forces from below. The carbon dioxide sits there like a fingerprint left by the ocean, pressed into the ice by whatever upwelling process reshapes this terrain. The fresh ice sits there as evidence that the process is ongoing. The salts sit there as a chemical signature of what kind of ocean lies below. If you wanted to design a landing site for a future Europa lander, a mission that could one day drill through the ice and sample what's underneath, Terra Regio would be at the top of the list. Webb effectively drew an X on the map, and in planetary exploration, an X on a map is worth more than 1,000 theoretical models. If you could somehow stand on Europa's surface and look up, if you could survive the radiation long enough to turn your head, the sky would be dominated by Jupiter. Not a dot, not a bright star, a wall. Jupiter would fill nearly 24 degrees of the sky, roughly 48 times the apparent size of the full moon as seen from Earth. It would hang there, banded in oranges and browns and whites, slowly rotating, the great red spot drifting across its face like a wound that never heals. Its 4 largest moons, Io, Ganymede, Callisto, and Europa itself, if you could see it from outside, would be strung along its equatorial plane like beads on a wire. And you would feel, in a way that no photograph can convey, just how small Europa is. how completely it exists at the mercy of that enormous planet. The tides that keep the ocean liquid, Jupiter. The radiation that sterilizes the surface, Jupiter. The gravitational resonance that locks its orbit, Jupiter. The very conditions that make its ocean possible are the same conditions that make its surface lethal. That tension is the central fact of this moon's existence. A gas giant that nurtures a hidden ocean with one hand and bombards it with radiation with the other. From promising to compelling. What Webb changed. What has changed, genuinely and measurably changed because of James Webb, is the strength of the scientific case. Before 2023, Europa was a promising candidate in the search for habitable environments beyond Earth, a place on the list, a moon worth studying. But promising in science means you have a hypothesis with supporting circumstantial evidence. It means the door is open, not that anything has walked through it. After Webb's carbon dioxide detection, after the confirmation that the ocean's chemistry is actively reaching the surface, after the tightened constraints on plume activity, after the sharpened target maps for Clipper, after the salt signatures and the fresh ice and the correlated spectral data, Europa has moved from promising to compelling. And the difference between those two words is the difference between a hypothesis and a research program, between a possibility and a priority. We now have specific, testable predictions about what Clipper should find when it arrives in 2030. We have a named location where ocean material appears to be directly accessible at the surface. We have a chemical ingredient list that keeps growing with each new analysis of Webb's data. We have converging evidence from multiple independent research teams using different analytical approaches reaching the same conclusion. Somewhere in that tension, in the gap between a surface that destroys organic molecules and an ocean that might produce them, there could be an answer to the oldest question our species has ever asked. What would we find if we could actually sample that ocean? Not infer its composition from surface deposits, not model it from orbital data, but scoop up a vial of Europa's ocean and analyze it in a laboratory. If there are amino acids, if there are lipids, if there are any of the molecular signatures that life produces on Earth, even without cells, even without anything recognizably alive, even just the building blocks assembled in the right configurations, it would be the most consequential discovery in the history of science. Not because it would prove life exists on Europa, but because it would prove that the chemistry of life is not unique to Earth. That the universe generates these molecular building blocks wherever and whenever the conditions allow. That we are not a cosmic accident. That the emergence of complex chemistry from simple ingredients is something the universe does routinely, given enough time and the right environment. That we are not alone in our ordinariness. What comes after, Clipper, is not the end of the story. It's the next chapter. If its 50 flybys confirm what Webb has suggested, if the carbon detection holds up at close range, if organics appear in the ice, if SUDA catches something extraordinary in a single grain of ejected material, then the scientific case for a Europa lander becomes essentially unanswerable. A lander mission to Europa has been discussed and designed and debated for years. The challenges are formidable, landing on a geologically active surface covered in ice spikes and ridges, surviving a radiation environment that would kill an unshielded human in hours, drilling through potentially 30 kilometers of ice to reach the ocean below, a technical challenge that dwarfs anything we've ever attempted in space exploration. The ice drill alone would be an engineering achievement comparable to building the telescope that started this entire story. But the scientific return would be commensurate with the difficulty. If a lander touches down on Terra Regio, on the X that Webb drew, and deploys a drill and melts through the ice and lowers an instrument into water that has never seen sunlight in the 4.5 billion years of this solar system's existence, Whatever that instrument finds will rewrite our understanding of life in the universe. Maybe it finds nothing. Maybe the ocean is beautifully, perfectly sterile, chemically interesting, physically dynamic, but biologically empty. That would still be important science. That would tell us something precise about the conditions required for life to actually emerge, not just the conditions required for life to be possible. A confirmed sterile Europa would mean that chemistry alone isn't enough. That something else, some additional ingredient, some specific circumstance, some improbable chain of events, is required for life to cross the threshold from complex chemistry to self-replicating biology. Even a negative result, rigorously obtained, is a scientific result of the highest order. It would constrain our models of life's origins in ways that decades of laboratory experiments have failed to do. Or maybe it finds something. Maybe the instrument reports molecular structures that have no inorganic explanation. Maybe the mass spectrometer identifies amino acid combinations that only biology produces. Maybe the concentrations of certain organic compounds are orders of magnitude higher than any geochemical process can account for. Maybe, in the most extraordinary scenario our species has ever contemplated, the cameras see something move. And then we will know that the universe is not empty, that it never was. The weight of the question. I want to take a moment to step back from the technical details and acknowledge what's actually happening here. We are, right now, in the early stages of answering the question that human beings have been asking for as long as we've been capable of asking questions. Are we alone? For most of history, that question was unanswerable in principle. We could speculate. We could philosophize. We could look at the night sky and feel the weight of possibility. But we had no method, no instrument, no experiment that could, even in theory, produce a definitive answer. The question lived in the domain of religion and poetry and late-night conversations, not in the domain of testable science. And now it does. Right now, a spacecraft is coasting through the outer solar system toward Europa. Another is circling Jupiter's moons. The most powerful space telescope ever built has detected carbon in an ocean we cannot directly see. The pieces of an answer are assembling themselves, one instrument, one flyby, one spectral signature at a time. We might be the generation that finds the answer, not the generation that builds the tools. That generation built Webb, launched Clipper, designed JUICE. But the generation that reads the results, that lives through the moment when the data comes back from Terra Regio, and scientists sit with it for weeks, checking it against every alternative explanation, running it through every model, looking for the false positive, and find that there isn't one. I don't know what that moment will feel like. I don't think anyone does. It might feel quiet at first. A press conference, a paper in a journal, careful, measured language from scientists who have spent their careers being wrong before and don't want to be wrong again. And then, gradually, as the magnitude of what the data says becomes undeniable, a kind of silence spreading through the world. Not the silence of nothing happening, but the silence of everyone, everywhere, trying to absorb the fact that everything just changed. Europa didn't ask for our attention. It didn't erupt dramatically like Io or parade its lakes openly like Titan. It kept everything hidden under ice and let us guess for 400 years. From Galileo's first glimpse to Hubble's shaky plume detections to Webb's patient, meticulous reading of chemistry from 600 million kilometers away. For 20 years after Galileo's spacecraft first measured that magnetic anomaly and gave us the ocean, we guessed. We modeled. We theorized. We wrote papers with careful, hedged language about conditions potentially suitable for life. And then Webb looked carefully, patiently, with instruments built for exactly this kind of subtlety. And Europa finally gave us something real. The ice hasn't cracked yet. Not for us. but Clipper will get closer than anything we've ever sent. SUDA will catch grains of ice no larger than a sand grain and read them like messages from the deep. Reason will peer through 30 kilometers of ice and map what lies beneath. And one day, maybe in the 2040s, maybe later, whenever the engineering catches up with the ambition, a lander will touch down on that fractured, irradiated, geologically churning terrain. A drill will begin its long, slow descent through the ice, and an instrument will enter water that has been sealed away from the universe for longer than multicellular life has existed on Earth. Whatever it finds down there, whether it's barren salt water or something stranger, something that rewrites every biology textbook ever written, will transform our understanding of where life can exist in this universe. And by extension, it will transform our understanding of what we are and whether we are alone. For now, we wait. But for the first time in the history of this search, we are waiting with evidence. Not just hope, evidence. If this video made you see Europa differently, if you feel that shift in your chest that comes from realizing the universe might be more alive than we thought, hit the like button right now. It takes 1 second, and it genuinely helps this channel reach more people who deserve to feel exactly that. You'd be surprised how much one click matters for a channel like this. And if you're not subscribed yet, I want to ask you seriously, what are you waiting for? Every week we dig into stories exactly like this one, where the science is real, the stakes are cosmic, and the answers are still being written in real time. Subscribe, turn on notifications, come be part of the community of people who stay curious about the universe, even when, especially when, the answers are difficult. I have a question for the comments. Do you think Europa has life? Not might have. Do you think it does? And follow-up. If Clipper finds definitive evidence of organic molecules in Europa's ice during its flybys starting in 2031, what do you think happens next? How does the world react? Leave your answer below. I read every single comment, and I respond to as many as I can. The discussion in the comments on videos like this one is genuinely one of my favorite parts of making this channel. Thanks for watching. I'll see you in the next one.